All right, everybody, what's going on? This video here, we're going to look at equations of lines and planes, and I'm guessing this is probably going to be a pretty long video. So let's go ahead and get started. So let's first look at the equation of lines, and then we'll look at planes. All right, so let's suppose we have, let's draw a picture of it. There's X, there's Y, and then this will be our Z axis. All right, so let's draw some line in here, L. So we'll call this line L right here. And we want to know the equation of this line. So let's put a point on here. Let's do this in green. So we'll call this vector here R0, R sub 0. And this is the point P0, which is X0, Y0, Z0. And then we have another point here. We'll call this point P, which is X, Y, Z. And let me move this up a little bit. All right, so we'll call this vector here R. And then we have another vector like this. We'll call this V. This vector V here is parallel to this line L. Okay. And so there's a vector that goes like this. We'll call this vector A. Okay. Now, vector V and vector A are parallel. All right. And of course here we've got the origin there. All right. So if we look at this, okay, if we look at this, we've got vector R. That's this vector here is the vector X, Y, Z. And we have vector R sub 0 is equal to the vector X0. Is X0, Y0, Z0. And we'll have vector V. Well, that's equal, we'll say that's equal to vector A, B, C. It's some vector parallel to line L. All right. Now, keep in mind that vector A and vector V, those two vectors are parallel. So we can actually say that vector A is equal to some scalar T times vector V. Okay, they're different lengths, aren't they? See that? So we can multiply T by something to get A, to get vector A, because A and V they're parallel. Now, vector R, let's look at it again. Vector R. Okay. So what is vector R? Well, do you remember back when you learned how to do vectors? So if we want to get vector R, that's vector R0 plus vector A, right? So let's do this in a little bit different color. So if I do this and bring this down like this. Remember that? The parallelogram method. You can do that, or you can, remember, if you put the tail of the vector, or the initial point of the vector, at the terminal point of another vector, then the resultant, or the sum of those vectors, is from the initial point of r sub 0 to the terminal point of a. So we can actually say vector r is vector r sub 0 plus vector a, right? And so we can say that vector r is equal to vector r sub 0 plus, now what is a? A is t times vector v, okay? And so what is this? This is the vector equation of the line, okay? It's the vector equation of the line. And keep in mind here, t, okay? T is a parameter that gives the position of vector r of a point on L. So basically what it's saying is, as t varies, the line is traced out by the tip of vector r. So we know a is equal to t times v. So as t changes, it's traced out by the tip of this vector, okay? And it can be negative and come back this way if t is less than 0. And then if t is greater than 0, it goes this way, okay? All right, so let's look at another equation for that line. So that's the vector equation. So what about parametric equations? Okay, what if we want to look at the parametric equations of a line? Well, let's just look at this right here. Okay, we've got vector r, which is what? X, Y, Z. So that's vector X, Y, Z is equal to vector r sub 0, which is this vector. So that's x0, y0, z0, plus t times vector v. So that's going to be t times vector v, which is ABC. And then that's going to give us x, y, z is equal to, so I'm going to distribute the t, so that's going to be TA, right? Or AT, however you want to write it, BT and CT when I distribute that. So I got x0 plus AT plus y0 plus BT plus z0 plus CT. All right. Now, how are these two sides here equal? Okay, how are they equal? Well, I don't know what I did there. Those should be commas right there. How about that? All right. When we add the two vectors, I don't know why I put a plus. Please excuse that. All right. So now, how do we know when these two vectors here are equal? Well, it's when their components are equal. So x has to equal this. So x equals x0 plus AT. Y is equal to y0 plus BT. And z is equal to z sub 0 plus CT. All right. And what does that give us? Well, that gives us our parametric equations. and I have that written here. So parametric equations for a line through the point x0, y0, z0, and parallel to the direction vector ABC are this. All right, so that's kind of interesting there. So what does that tell us? That when we're dealing with the equation of a line, or we're looking for the equation of a line, we need what? Well, we need a point on the line, and we need a direction vector that's parallel to the line. Okay? And so the direction vector that's parallel to the line, the components, that's the coefficients of t, and the point on the line, that's the x0, y0, z0. All right, so let's now look at some examples. Okay, so far we've got, we know the vector equation, and here we've got our parametric equations. So, I don't know, the problem may ask you to find the vector equation of the line. It may ask you to find the parametric equations of the line. And as you'll see in a little bit, it may ask you to find the symmetric equations. That's going to be another one. We'll do that in a little bit. Okay, so let's look at part A here. It says find a vector equation and parametric equation, so it's asking for both, for the line that passes through the point 5, 1, 3 and is parallel to the vector I plus 4j minus 2k. All right. Well, that's nice, because it tells us, it basically tells us everything, doesn't it? You see that? It tells us everything. So we want the vector equation first. So part A, we've got r is equal to r sub 0 plus t times vector v. All right, so I need vector r. So what is vector r? Well, vector r, remember back up here, the point through the line. See this x0, y0, z0, that's this. R sub 0 is that vector. Okay, and so we get r0 is equal to 5i plus j plus 3k. I just wrote it in the form ijk. All right, plus t times vector v. Okay, so what is t times vector v? And I understand you may not want to show all this work, and I guess that would be fine. I'm just writing it down so you can see it in the video. So I need t times vector v. Well, where's vector v? Remember, vector v is the vector parallel to the line. So this right here is vector v, and I've got to do t times that. Okay? And so, we can write it, well, let's do it like this. Let's do this. Let's do vector r is equal to vector r0, which is this vector, so that's 5i plus j plus 3k plus t, okay, that's vector r0 plus t times vector v, which is this vector, I plus 4j minus 2k. And so this is going to be r is equal to 5i plus j plus 3k plus ti plus 4t, whoop, no vector there, plus tj minus 2tk. And so I'm going to group the I terms together so you can see the I and I factor that out. That's going to leave me with 5 plus t times vector I plus, and then the j, that's going to be 1 plus 4t, 1 plus 4t times vector j plus, and now for the k, that's going to be 3 minus 2t, 3 minus 2t times vector k. And so this is the vector equation for the line. And see, we didn't have to do much with this because they gave us a point on the line and they gave us the parallel vector. Okay? So that's, you know, so there you have it. All right? And I also want you to keep in mind, I didn't write it, but remember, this is x0, y0, z0. And then remember, the coefficient of I, that's, well, let's write this vector. This vector in the component form, that's going to be 1, 4, negative 2. And so this is your A, this is your B, and this is your C. Okay. All right. So for part B, okay, so for part B, we know x is equal to x0 plus at, y is equal to y0 plus bt, and z is equal to z0 plus ct. And so we know that's 5 and a is 1. So we get x is equal to 5 plus t. Y is equal to, well, what's y0 and b? Well, that's 1 and 4. And so that's 1 plus 4t. And then z, well, what's z0 and c? That's 3 and negative 2. So that's 3 minus 2t. And here are your parametric equations. And notice this, it's right there. Okay. All right, so that answers part A of the problem. So what about part B? It says find 2 other points on the line. 2 other points on the line. All right, so, and actually this is not part B, this is still part A. Part B is down here. All right, so let's find 2 other points on the line. Okay, well, I need a x, y, and a z, right? Well, what's my variable that's changing? That's t. So how about I just say, okay, t equals 1. Well, you might ask, well, why did you choose 1? Well, I just wanted to. You can choose whatever you want for t. Okay? So that's going to give me x is equal to 5 plus 1, which is 6. All I'm doing is taking the 1 and plugging it into here, and that's giving me my x coordinate. And so y is equal to 1 plus 4 times 1, which that's 5. And then z is equal to, that's going to be 3 minus 2 times 1, which is 1. So that gives me the point 6, 5, 1. So there's a point on the line. And now let's get another point on the line because it asked for 2. So just use negative 1. Yeah, you can use 0 if you want, but let's just use negative 1. So I've got x equal 5 plus negative 1, which is 4. I've got y equals 1 plus 4 times negative 1, which that's what, negative 3. And z equals 3 minus 2 times negative 1, which that's 5. And so that's the point 4, negative 3, 5. And there's your answer. All right, and then something I want to note. I'm not going to go through working it, but note that the vector equations and parametric equation are not unique if we change the point parameter or parallel vector. Okay. So basically what we've got here, and I'm not going to go through it. So if we change the point or the parameter or choose a different parallel vector, okay, because there's more than one vector that's parallel to that line. Okay. I mean, it doesn't have to necessarily start at 0, 0, 0. We can move it anywhere. So, for instance, if we use, say we use the point 5, 1, 3. Okay. If we use the point 5, 1, 3. Then we would get different parametric equations. Or, well, no, I'm sorry. Wait a minute. Let's see. That's what we did do. We did do 5. I'm sorry. Not 5, 1, 3. If we chose 5, 1, 3, but let's say instead we use the point 6, 5, 1. We use this point because we know that point's on the line, right? That point's on the line. So if we chose that point instead, we would get different parametric equations. Okay, so I just wanted you to be aware of that. All right. Now let's look at this. If a vector v, a, b, c is used to describe the direction of a line L, that's your parallel vector, then the number a, b, and c are called direction numbers of L. Since any vector parallel to v could be used, we see that any three numbers proportional to a, b, and c could also be used as a set of direction numbers for L. Another way of describing a line is to eliminate the parameter t. If neither a, b, or c is 0, we can solve for t. And these equations are called symmetric equations. Okay? So basically what's going on here is, in our parametric equations, we have x is equal to x0 plus at. We have y is equal to y0 plus bt. And we have z is equal to z0 plus ct. And so if we solve each of these for t, okay, so that's going to be x minus x0 equals at. So t is equal to x minus x0 over a. And then similar, we get y equals y minus y0 over b. And z equals z minus z0 over c. we solve for each one. So our symmetric equations are x minus x0 over a is equal to y minus y0 over b, which is equal to z minus z0 over c. And so these are your symmetric equations. All right, so let's look at another example. It says find parametric equations and symmetric equations of the line that passes through the points A and B. And then for part B, at what point does this line intersect the XY plane? All right. So we need what? We need a point on the line. Well, we got two of those, don't we? You see that? We've got two of those. So what do we need now? We need a vector that's parallel to the line. Okay? We need vector parallel to our line. Well, that would be what? Well, we know those 2 points are on there, so are on that line, so vector AB would be parallel to our line. So remember how to find vector AB? That's 3 minus 2, negative 1 minus 4, and 1 minus negative 3. And so we get vector AB is equal to 1, negative 5, 4. Okay. Now, let's use point A. Well, you know, if you wanted to, you could use point B. It's on the line also. Let's just use point A. So we're going to use vector A, and we're going to use point. Well, we're going to use point A. We're going to use, and we've got our parallel vector AB. Okay. So look, the parametric equations. Parametric equations. We need what? A, B, C, x0, y0, and z0, right? So we've got A is equal to negative 1, B is A is equal to 1, B is equal to negative 5, and C is equal to 4. And then we have x0 is 2, y0 is 4, and z0 is negative 3. And remember what the parametric equations are. Let's just write it down again. Y is equal to y0 plus bt, and z is equal to z0 plus ct, right? That's our parametric equations. We saw that earlier. So look, all you're doing is plugging that in. So I've got x is equal to 2 plus t. I get y is equal to 4 minus 5t. And I get z is equal to negative 3 plus 4t. And here are your parametric equations. And now they want symmetric equations. That's just this. You see that? Now our symmetric equations is x minus x0 over a equals y minus y0 over b, which equals z minus z0 over c. Well, there you go. Plug all that in. So that's going to be x minus 2 over 1 equals, and then I've got y minus y0, y minus 4 over negative 5, which equals z, and that's going to be plus 3, because we got a negative there, over 4. And so here are your parametric equations. And see how easy all this stuff is? You just gotta, you've got to know the format that your vector equations are in, your parametric equations and your symmetric equations. You've got to know this. Okay? You've got to know this. And you've got to know this right here for your vector equation. And you've got to know that R is the vector x, y, z. You got to know that your point is x0, y0, z0. And if you're doing the vector equation, you got to know R0 is just that vector. And then you got to know vector v is a, b, c. That's what you've got to know. You get the test, you get your test, write it down. Okay? Is that the problem? Yeah, okay, that's a different. All right. So there's part A. Now we need to do part B, which says at what point does this line intersect the XY plane? Okay. So let's give that a shot. Let's come down here. Just kind of divide this up a little bit. See if we got enough room there. All right, so for part B, when does this intersect the XY plane? That means it's in the XY plane. When it intersects it, what's the XY plane? Well, that's when z is equal to 0, right? So what can we do here? Well, let's plug 0 in for z. So I get x minus 2 over 1 equals y minus 4 over negative 5 equals, now what am I doing? I'm plugging 0 in for z. So that's going to be 3/4, right? And so now I've got x minus 2 over 1 is equal to 3/4. Right, because all three of them are equal, so I'm going to set this equal to 3/4. So when I solve that for x, I get x equals 11 over 4. And then I'm going to take y minus 4 over negative 5, set that equal to 3/4. And so that's going to give me y minus 4 equals negative 15 over 4. So y is equal to 1/4. So there's your point. Your x is 11/4, your y is 1/4, and what was z? It was 0. And so that's the point where that line intersects the xy plane. Okay? If you looked at it, I don't have a lot of room here. Let's see if I can kind of maybe squeeze it in here. So, just say you got a point right here. Let's just say that's the point. I don't know. It's somewhere in there. Okay. But then, you got your line coming in like this. Your line's coming in like this. And that's what we're looking for, where it intersects that XY plane. Okay. All right. I didn't leave myself a lot of room on working that problem, did I? All right, so let's look at our next example. Show that the lines L1 and L2 with parametric equations. Okay, so here's the parametric equations of our lines. Notice up here they're using T, and here they're using S, just to let you know, just to distinguish the two lines. And we want to show that lines L1 and L2 with these parametric equations are skewed. Okay, So what does that mean? Well, that means that they don't intersect and they're not parallel. Okay? So, two lines can be parallel without intersecting. Okay? So how are we going to go? How are we going to go about this? Well, I don't know. They may not intersect. So are they parallel? Let's check and see if they're parallel first. So how in the world can I show that the lines are parallel? Well, we can show that they're parallel by showing that their direction, or show that they're not parallel, or parallel. They may be, I don't know. But we can show it by showing that their direction vectors are not parallel or parallel. Okay, remember your vector V, the vector that's parallel to those lines. So if I have a vector parallel to line 1 and a vector parallel to line 2, well, if those two vectors are parallel, the lines are parallel. If those two vectors are perpendicular, the lines are perpendicular. And if those two vectors are neither one of those, then the lines are skewed lines. All right, so what's my direction vector? Remember, that's like your vector v1, right? It's vector v, but let's just call it v1 since, I don't know, since we got two lines, we'll call this one v1. Remember, that's your a, b, c. So that's vector 1, 3, -1, and vector v2, the direction vector for this one, that's going to be the vector what? 2, 1, 4. And so we know that these are parallel if what? So let's do 1, 3, -1. Remember this? If the cross product of those two vectors is equal to 0, then that means they're parallel. If it doesn't equal 0, it means they're not. All right, so that's going to be what? That's the determinant I, J. Still remember how to do the cross product. Let's hope so. That was the lesson before this one. All right, so this is going to be what? So that's going to be 12 minus -1 times vector I minus, remember the signs change, and so we're doing vector J, so that's what? That's 4 minus -2 times vector J plus, and now for K, that's going to be 1 minus 6 times vector K. And so that is going to actually give us 13I minus 6J minus 5K. So not parallel. We didn't get the 0 vector, did we? All right. So what could we do now? Well, what if we set up equations? So that's X, that's Y, and there's Z, right? We've got X, Y, and Z. So let's set X 1 plus t equal to 2s, this equal to this, and this equal to this. So let's try that. So that's going to be 1 plus t equals 2s, negative 2 plus 3t equals 3 plus s, and 4 minus t equals negative 3 plus 4s. So all I did is I set this equal to this equal to this, and this equal to this. All right. Now, let's do this. Let's take this equation and this equation. Okay, so let's take these two equations. And so that's going to give me t minus 2s equals negative 1. So I just brought the 2s over and the 1 over here. And then for this one, that's going to give me 3t minus s, going to bring the s over here, and then I'm going to add the 2 to both sides, and that's going to give me 5. And so now let's solve these using using elimination method. So let's multiply this by negative 2. So that's going to be t minus 2s equals negative 1, and negative 6t plus 2s equals negative 10, and add those. So that's going to give me negative 5t equals negative 11. So I get t equals 11 over 5. All right, so that's t. But now let's go ahead and see what s is. So I'm going to take the 11/5 and plug it into here. So that's 11 over 5 minus 2s equals negative 1. So that's going to be negative 2s, subtract 11/5 to both sides. That's negative 16 over 5. Multiply everything by negative 1/2. So s is equal to 8 over 5. So those are that s and t, that satisfies those first two equations. But now, let's plug these in because we've got 3 sets of equations, don't we? We've got this one right here also. So we should be able to take 11 over 5 and 8 over 5, plug into this equation, and get the same thing on both sides. So let's see what happens. So 4 minus 11 over 5 equals negative 3 plus 4 times 8 over 5. And so that's going to be, that's 9/5 over here on the left side minus 3 plus 32 over 5. So that's 9/5 equals, and that's going to be 17 over 5. Oh, those, it doesn't satisfy that last equation, does it? All right. So that tells us, so there are no values of t and s that satisfy the 3 equations. So L1 and L2 are skew lines. There you have it. Okay, so we showed that they were skew lines. All right. Okay, so that's lines. Okay. Now let's look at planes. Okay. And this lesson here, I know it's a long lesson. Your teacher may split this up into 2 class meetings. Okay, so if that's the case, they'll probably teach the first class meeting down to this, and then the next class meeting they would pick up right here. So this may be your second class meeting, and this talks about planes. Okay. All right, so this is a plane. So let's look and see what we have here. All right, so a plane, okay, So let's say we have a single vector that's parallel to a plane. Okay, well, that's really not enough. Okay, that's not enough for the direction of the plane. Okay, having a vector that's parallel. But what if we have a vector perpendicular to the plane? Okay, so let's suppose that we have 2 points. See this, P0 and P. Okay, P0 and P. They're points on the plane. Okay, P0 and P, they're points in the plane. And so if I draw a vector N, okay, a vector N that's perpendicular to the plane at this point P0. Okay, now I have a vector R0 that goes to point P0, and I have a vector R that goes to point P. All right, so N is perpendicular or orthogonal to the plane, and it's orthogonal to every vector in that plane. Okay, and it's also perpendicular or orthogonal to vector R minus vector R0. Okay, and N is also called the normal vector. Okay, the vector that's orthogonal, it's the normal vector. All right, so we know that if the N is perpendicular to this vector, okay, or to this, then we know, since they're perpendicular, we know vector N dot we know the dot product of those is 0, right? And so we could also write vector N dot vector R is equal to vector N dot vector R0. I just distribute and then move that over. Okay. And these two equations are called the vector equation of the plane. Okay. These are either one's called the vector equation of the plane. All right. Now, we also have the scalar equation of the plane. So let's look at getting the scalar equation of the plane. So we've got vector N. We'll say that's A, B, C. We've got vector R, which is, we'll call that X, Y, Z. And we have vector R0 is equal to X0, Y0, Z0. Okay, see, I got my vector R is X, Y, Z. My vector R0 is X0, Y0, Z0. And then vector N, we're calling that vector ABC. All right, so what do we have up here? We have what? The dot product of N and vector R minus vector R0. So if I do the dot product of these two, okay, So I'm going to do the dot product. So that's going to be the dot product of A, B, C dot. Now, what's R minus R0? Well, that's what? X minus X0, Y minus Y0, and Z minus Z0. And so if I do the dot product, that's going to be what? That's going to be A times X minus X0, right? I do this times this, plus this times this, B times Y minus Y0, and then C times this, plus C times Z minus Z0. Oh, and this equals 0, and that equals 0. And so this is your scalar equation for the plane, which I have written up right here. It says a scalar equation of the plane through point P0 with normal vector n, ABC, is this. You got to know this. You see that? You've got to know that. All right. So we just got finished doing lines, and in order to get the equation of a line, you notice that we needed what? We needed a point, and we needed a vector parallel to the line. Well, look at this. For the equation of a plane, we need a point on the plane, and we need the normal vector to the plane. We need a vector that's normal to the plane. That's what we got to have. And you can see your point x0, y0, z0, well, that's here. And then your normal vector, there's A, B, C. See that? All right. So there's another way that we can write this line. Okay, there's another way to write the line. And it's called a linear equation. I'm sorry, I said line, I meant plane. It's called the linear equation. Okay? So we're talking about planes now. I guess I still got my mind on those lines up there. But look at this. If I distribute, clear all those parentheses. So I got AX minus A times X naught plus BY minus B times Y naught plus CZ minus C times 0, Z0 equals 0. And so that's going to give me AX plus BY plus CZ minus, now what I'm going to do here, I'm going to take this, let's see, where is it? I'm going to take this, this, and this. I'm going to group those together, but I'm going to factor out a negative, and I'm going to put AX0 plus BY0 plus CZ0 equals 0. Okay, and I'm going to write this as AX plus BY plus CZ plus D is equal to 0 plus some constant. And what I'm doing here is we're calling this term here, we're calling that D. Okay, because you know when you distribute all that, these numbers here, they're just constants, and you're going to combine them into one number. We're just going to call that D. Okay, and so this is your linear equation. Okay, and one thing to notice is, let's notice. Okay, notice that normal vector n, okay, n is a, b, c, right? That's what? That's the coefficients of x, y, and z. See, there's your normal vector right there. They're the coefficients of x, y, and z. Okay? So if they did give you this equation of a plane in this form here, well, you know what the normal vector is. That might come in handy. Okay? And so this is the, let's write the, well, you know, this is the scalar form or scalar equation of a plane. This is the linear equation of the plane. And then back up here, where is it? Well, I wrote that already. This is the vector equation of the plane. All right. All right, so let's look at an example. So it says, find an equation of the plane through the point 2, 4, -1 with normal vector n equals 2, 3, 4. Find the intercepts and sketch the plane. So they're wanting us to find the equation of the plane. Now, remember what I said. What do we need to find the equation of the plane? We need a point on the plane, which, look there, they gave us that. And we need the normal vector. They gave us that also. So they give us everything we need for this one. See, here is your A, B, C, and here's x0, y0, z0. So you got everything. And so what's the equation of the plane? That's a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 1. Not equals 1, equals 0. There's the equation. Now all you're doing, this second grade stuff, now just plug it in. And so that's going to be 2 times x minus 2 plus 3 times y minus 4 plus 4 times z plus 1 equal 0. And then I'm going to distribute 2x minus 4 plus 3y minus 12 plus 4z plus 4 equals 0. And so that's going to give me 2x plus 3y plus 4z minus 12 equals 0. So that's going to give me 2x plus 3y plus 4z equals 12. Just move the 12 over. All right. So there you go. There's the equation of the plane. That was easy because they just came out and said, here's your point, here's your normal vector. We didn't have to do anything except plug numbers in. They're not all going to be that easy. All right, so that was the first part. Then it says find the intercepts and sketch the plane. All right, so we want to find the intercepts. So this is the next part. So the x-intercept, okay, so what's the x-intercept? That's when that point is on the x-axis. So that means what? That means y is equal to 0 and z is equal to 0. Well, look at this. This isn't rocket science, is it? Plug 0 in for y and z and solve for x. Okay? So we've got 2x plus 3 times 0 plus 4 times 0 equals 12. So 2x equal 12, x equal 6. All right? And then we can do the same thing for the y-intercept and the z-intercept. So the y-intercept, well, it's on the y-axis. So that means what? X is 0 and z is 0. And so I've got 2 times 0 plus 3y plus 4 times 0 equals 12. So 3y is 12, y equals 4. Oh, and let's go ahead and write the points. So there's that point, right? Y and z are 0, x is 6. This point would be 0, 4, 0. And now for the z-intercept, well, that's what? It's on the z-axis. So that means what? That means x is equal to 0 and y is equal to 0. And so that's going to be 2 times 0 plus 3 times 0 plus 4z equals 12. So 4z equals 12, z equals 3. So that's the point 0, 0, 3. And what did it ask us to do? It said sketch the graph. So let's see. How about we see if we can come right in here and do it. All right, 1, 2, 3, 4, 5, 6. So there's the point 6, 0. 1, 2, 3, 4. There's the point on the y-axis. Go to where that, and then 1, 2, 3, and there's the point on the z-axis. And so we can sketch. We sketch the plane. Okay. So there's your plane that lies in the or the portion of the plane. There's a portion of the plane that lies in the first, and what's that called? That's in the first, remember? Octant. Remember that? That's from a couple of videos back. And so there you go. There's your graph and your intercepts. All right, so let's look at this one. Find the equation of the plane that passes through the points 1, 3, 2, 3, negative 1, 6, and 5, 2, 0. All right, so think about it. What do we need? We need a point on the plane. Do we have that? Yes, we got 3 of them. Okay. Well, what's the other thing we need? We need a normal vector, don't we? We need the normal vector to the plane. All right, so let's see if I can sketch this out a little bit. And I'm not going to try to get too accurate with it. I'm just going to kind of give you a picture of it. So let's plot the point 1, 3, 2. So I'm going to come down 1 and then 3. That's going to intersect about right in here. And then I'm going to go up 2. So I'll have that point about right in here. That'll be point P. 1, 3, 2. Okay. And then let's plot Q. So I'm going to go 3 and then negative 1 going this way. So they're going to intersect about right in here. And then we go up 6. And so that's probably going to be a point about right in here. So Q is going to be 3, negative 1, 6. And I'm just sketching this kind of rough. And then we've got the point 5, 2, 0. So we're going to come down 5, go out this way 2. And that's going to intersect about right in there. And Z is 0. And so I have this. And this is point R. That's the point 5, 2, 0. Okay. So what do I need? Okay. What do I need? Well, look at this. I've got a vector PQ, right? And I've got this vector PR. You see that? I've got those two vectors. And what do I need? And I know those two vectors are on the plane, right? Those two vectors are on the plane. Or lie on the plane. So, oh, that's right. If I take the cross product of these two vectors, that gives me a vector that's perpendicular to both of those. So that means it would be perpendicular to that plane. Well, there we go. Okay, so let's get vector PQ. Okay, so what is vector PQ? That's 3 minus 1, negative 1 minus 3, and 6 minus 2. And that's going to be the vector 2, negative 4, 4. And then if I take the vector PR, this vector, that's 5 minus 1, 2 minus 3, and 0 minus 2. And that's going to be the vector 4, negative 1, negative 2. So there you go. Now we just do the cross product. All right, because we have a point on the plane. We just need the normal vector. That's what we're finding right now. Okay. All right, so what is that going to be? I, J, K, and that's going to be 2, negative 4, 4, 4, negative 1, negative 2. The cross product comes in handy, doesn't it? It helps us out a lot. All right, so for I, that's going to be 8 minus negative 4 times vector I minus, remember the signs alternate, so that's going to be negative 4 minus 16 times vector J plus, and then I've got negative 2 minus negative 16 times vector K. And so this is going to be the vector 12I plus 20J plus 14K. So there's our normal vector. Okay, so that's our normal vector. And so let's use, so our normal vector n, so n, vector n, that's 12I plus 20J plus 14K. And then, let me erase that. And then I've got my point that I'm going to use. I'm going to use this point right here, 1, 3, 2. So that's 1, 3, 2. So look at there. There's A, B, C, and there's what? There's your x0, y0, z0. And so we plug it in. So I've got A times x minus x0 plus B times y minus y0 plus C times z minus z0 equals 0. And then I'm going to distribute, combine like terms, and that's going to, since I'm running out of room, I'm going to kind of leave a few steps out. You can do that. You can distribute, combine like terms, and that's going to end up leaving me with 12x plus 20y plus 14z equals 100. And so 6x plus 10y plus 7z equals 50. I just divided everything by 2. 2 went into everything. And so there's your equation of the plane. So just remember when you're doing this, when you're finding the equation of a plane, you've got to have a point on the plane and you've got to have the normal vector. Okay? All right. So next example, find the point at which the line with parametric equations this intersects this plane. All right, so we're looking for when does this line intersect this plane? When does it go through? So, you know, we got a plane out here and you got a line coming. You got a line coming through here like this, okay, and something like that. So what's that point? That's what we're looking for, okay. No, that wasn't that plane and that line. It was just to give you an illustration. Well, that's easy. Well, that's just what, 4 times x. Well, what's x? X is 2 plus 3t, right? We're just plugging these in for x, y, and z. And then that's going to be plus 5 times negative 4t minus 2 times 5 plus t equals 18. All right, so we solve 8 plus 12t minus 20t minus 10 minus 2t equals 18. So combining like terms, that's going to give us negative 10t. Negative 10t minus 2 equals 18. So t is equal to negative 2. Okay. So what did that do? Did that give us the point? No, that didn't give us the point. That gave us t. That told us what t is. Now, to get the point, we've got x is equal to 2 plus 3 times negative 2. We're taking the negative 2 and plugging it in for t. And then we're going to do the same thing for y. That's negative 4 times negative 2. And then we're going to do the same thing for z, 5 plus negative 2. All right. And so this is going to give us x is equal to negative 4, y is equal to 8, and z is equal to 3. And so our point is negative 4, 8, 3. And there's the point where that line crosses through that plane. So that was easy. So, you know, if they want to know where do they intersect, you know, and you've got your parametric equations, just plug them in, solve for t, and then you take the t value and plug it back in, and that'll give you your x, y, z point. All right, so let's look at this. We've got 2 planes are parallel if their normal vectors are parallel. All right, so that makes sense. If you got 2 planes and you find the normal vector to each plane and those normal vectors are parallel, well, then the 2 planes have to be parallel also. All right, so that makes sense. And then we have, if 2 planes are not parallel, then they intersect in a straight line. And the angle between the 2 planes is defined as the acute angle between their normal vectors. Okay, so obviously if the planes aren't parallel, they're going to intersect. And you can see where this plane and this plane, where they intersect, see this line here? And then here's the angle between them. But look at this. This angle is the same as the angle between their normal vectors. So that's going to come in handy, because think about it. If we have 2 vectors and they want us to find the angle between those 2 vectors, do we know how to do that? Of course we do. You learned it in trig, finding the angle between 2 vectors, and you also learned it in calculus, the section on dot products. Okay, so you know how to do that already. So let's look at this example. So it says find the angle between the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1. We want to find the angle between them. And then it says find symmetric equations for the line of intersection L of these 2 planes. So they want us to find the equation of that line where those 2 planes intersect. All right, so So what did it tell us that we can do to find the angle between the two planes? We can just find the angle. We can find the angle between their normal vectors. Okay, so let's look at this. We can call this line 1, call this line 2, I guess. And so for part A, okay, the normal vector for this one, well, that's what? That's the vector 1, 1, 1. Oh, but wait a minute, where did that come from? Well, if you remember what I showed you earlier in the video, that the normal vector A, B, and C, that's the coefficients of x, y, and z. And so my normal vector, we'll call it to this plane, that's going to be what? 1, -2, 3. It's the coefficients of x, y, and z. So there's my two normal vectors. And so what am I looking for? I'm looking for the angle between the planes. So that means I can just find the angle between these vectors. And so remember, that's what? Cosine theta is equal to the dot product of n1 and n2 over the magnitude of n1 times the magnitude of n2. So there you have it. All right, so let's find all that. So let's see the dot product of the two vectors. Well, that's just going to be what? This 1 times 1 plus 1 times 3. I'm sorry, 1 times -2 plus 1 times 3 plus 1 times 3. And so the dot product is 2. And then I need the magnitude of n1. That's just the square root of 1 squared plus 1 squared plus 1 squared, which that's the square root of 3. And then the magnitude of n2, that's going to be the square root of 1 squared plus -2 squared plus 3 squared. And that ends up being, I think that's what, square root of 14. And so now we've got cosine theta is equal to 2, that's the dot product, over the square root of 3 times the square root of 14. Okay, just plugged everything in. Okay, and so this tells me that theta is equal to the inverse cosine of this, 2 over, and we'll say that's square root of 42. 3 times 14 is 42. And so that tells me theta is equal to, and that's going to be 72, about 72 degrees when we plug it in. So that's the angle between the two. All right, now what was part B? It says find symmetric equations for the line of intersection L of these two planes. All right, so what do we have to do? Well, first thing we need to do is we need to find we got to have a point on L, right? We got to find the point on L. All right, so for part B, we need a point on L on our line. All right, so, well, how about we just find a point in the XY plane? Okay, it didn't say what point we need. We can use any point. Or we can do any point on the line. Okay. So we'll just let z equals 0. Okay, so let's let z equals 0. So what we're going to do here is we're going to plug 0 in for z right here, and we're going to plug it in right here. And so that's going to leave us with x plus y equals 1 and x minus 2y equals 1. You see that? And you know, you don't have to do z equals 0. It's just easier to do that. So that gives us x plus y equals 1 and x minus 2y equals 1. So just solving a simple system of equations, we'll multiply by -1. So that's negative x minus y equals -1, and x minus 2y equals 1. So that's going to give me negative 3y equals 0, y equals 0. All right, so z is equal to 0, y is equal to 0. What's x? Well, I can take the 0 and plug it into here. So x plus 0 equals 1, so x is 1. So we know the point 1, 0, 0 lies on L. All right. So find symmetric equations for the line of intersection L of these two planes. All right. So since L is in both planes, okay, L in both planes, it is perpendicular to N1 and N2. It's perpendicular. All right. So what do we need? What do we need to find the equation of a line? We need a point on the line, right? Which we have right there. And we need V that's parallel to the line. Okay. Well, if L is perpendicular to these two vectors, then if we do the cross product, okay, L is perpendicular, okay? L is perpendicular to these two vectors. So that means V would be perpendicular to these two, right? Because this has to be parallel with L. So V would be perpendicular because L is perpendicular. So all we need to do is find the cross product of this, and that will give us our vector V, which is parallel with L. All right, so let's see. So I'm going to do the cross product of N1 and N2. And so that's I'm running out. I didn't leave myself a lot of room in this video, did I? To work the problems. So all I'm going to do is I'm going to take N1 and N2 and I'm going to write those down there. So that's 1, 1, 1. And this is going to be 1, -2, 3. And so the dot product, okay, we ought to be, I'm not sorry, not the dot product, but the cross product. All right. And if I said dot product before that too, then I meant cross product. And so I'm just going to do this real quick. That's 3 minus -2. You should know how to do this by now. 3 minus 1 times vector J plus -2 minus 1 times vector, not vector J, vector K. And so that's going to be 5i minus 2j minus 3k. So this is your vector V right here. Okay. Now, so vector V, remember, that's your A, B, and C, right? Don't forget that. That's A, B, and C, those 5, -2, -3. And then your x0, y0, z0. That's x0, y0, z0. And so our symmetric equations, remember that's, let me change that's x minus x0 over a plus y minus y0 over b plus z minus z0 over c. And so that's just going to be x minus 1 over 5 equals y minus 0 over negative 2, which equals z minus 0 over negative 3, just plugging all that in. So that's going to give us x minus y over 5 equals y over negative 2 equals z over negative 3. And so there's your symmetric equations. Now, the other thing that I want you to know is, what if they asked you to find the vector equation or the parametric equations? Okay, what if they ask you to find that? The vector equation and the parametric equations. So let me erase this, and we will do that. We've got the symmetric equations, but let's find the vector and parametric also. I know they didn't ask it, but just for fun, let's do that. Okay, so I've got all of that erased and everything. So, but I did erase something I didn't need to. Here's the symmetric equations here. And here's our point. Here's our point 1, 0, 0. That's the point that lies on L. And then our normal, or our vector V. What was that? Now, we had V is equal to 5i minus 2j minus 3k. Okay, there's our normal vector. So just remember, this is what? This is x0, y0, z0, and there's a, or just remember your a, b, c. We can also write that 5, negative 2, negative 3, and there's your a, b, and c. So let's do the vector equation. So we've got r is equal to, remember, r0 plus t times vector v, which that's equal to vector r0, which that's going to be 1, 0, 0. That's this vector, the vector that goes from 0, 0, 0 to the point x0, y0, z0. So that's that vector, plus t times vector v, which is 5, negative 2, negative 3. Okay, and so that's going to be 1, 0, 0 plus, and that's going to be 5t, negative 2t, negative 3t, which, so that's going to give us, that'll give us vector r equals, and that's going to be 1 plus 5, 1 plus 5t. See, why did I put a vector over that? 1 plus 5t, and then 0 plus negative 2t, which is just negative 2t, and 0 plus negative 3t, which is just negative 3t. And so there's your vector equation. And yeah, I know earlier we did a problem like this where we did the vector equation and we wrote it different. I mean, you can write it like this. 1 plus 5t times vector I minus 2t times vector j, not plus, minus 3t times vector k. Now, if you want to write it like that, I don't guess it really matters. So that's your vector equation. Now what about our parametric equations? Well, your parametric equations, remember, that's x equal x0 plus at, y equals y0 plus bt, and z equals z0 plus ct. And so, well, here you go. Just plug everything in. But also, you got it right here, 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 and here. So x is just equal to 1 plus 5t. Y is equal to negative 2t, because y0 is 0, and z equals negative 3t. And so here's your parametric equation. So that's parametric equations. This is your vector equation. And this is your symmetric. So, so this problem, it's one problem where you're finding the equation of the line, but your teacher could ask you, find the symmetric equations, or find the vector equation, or find the parametric equations. Well, now you know how to do that. Okay. All right, so let's look at this. So we're getting close to the end. We've got this example and 2 more after that one. The last 2 examples won't take long to work. This one will probably take a little more time. All right, it says find a formula for the distance d from a point P1 to the plane ax plus by plus cz plus d equals 0. So we want to know the distance from a point to a plane. That's what we're looking for. All right, so let's just draw a picture here. Let's see, let's just kind of maybe something like that. And we got a point out here. We'll call that point P1, which is x1, y1, z1. And let's say we got some point in the plane. Okay, some point in the plane. And we'll call that point P0, which is x0, y0, z0. That's that point right there. And we're looking for something that's the distance here. This is vector n, your normal vector here. And you've got a line here, and then you've got a line here. All right. All right, so let's take a look and see what we've got here. All right. So what am I looking for? I'm looking for this distance right here. This distance d. That's what I'm looking for. And how in the world am I going to do that? Well, let's see. We've got a vector right here. Okay, we've got a vector. Let's write it here. P0, P1 is equal to the vector, and that's going to be x1 minus x0 y1 minus y0 and z1 minus z0. Okay, so that's this vector here, p0, p1. Just that minus that, that minus that, and that minus that. Yeah, this is a 0 down here. All right, so the distance d from P1, what is that? To the plane. What is that distance? Well, look at this. Think back to earlier lessons. This distance right here, that is what is the absolute value of the what? Scalar projection of vector P0, P1 onto, okay, the projection of this onto vector N. And N is equal to what? A, B, C, our normal vector. So remember that? Remember, if I take this vector, it's like you're shining a light down this way. And if this projection here, okay, it's the projection of this down here. The scalar projection, that'll give me the length of it right there. So if you remember, D is equal to the scalar, the absolute value of the scalar projection. So that's what? Remember what that is? P0, P1 onto vector N, which is equal to the dot product of N and P0, P1 over what? Over the length of N. And it's the absolute value, so I need to put that in absolute value. This up here has to be positive. Okay, I'm not worried about the denominator. The denominator is going to always be positive. It's under the square root. Okay, and so what do we have here? Well, that tells us that D is equal to, okay, the dot product of N and this. All right, well, let's look at this. Let's take this and kind of move it down some so we can see it. Let's see. Let me just kind of stick it right there. Can you see it? I think so. I don't know. This little right here. I don't know if this is... I don't know if that's cutting off or not. Anyway. Okay, so this is what we're looking at. This vector, we've got this vector and this vector. So it's the dot product of those two, right? So the dot product, that's just this times this. So A times x minus x1 minus x0. So that's A times x1 minus x0 plus B times y1 minus y0, B times y1 minus y0 plus C times z minus z0, or z1 minus z0. Okay, so that's the numerator all over the length of N. That's what? A squared plus B squared plus C squared. And it is absolute value. I'm just going to put it on the numerator. Denominator's positive. And so now let's multiply all of that out. That is going to be, let's see if I can squeeze it in here. It's going to be absolute value AX1 minus AX0 plus BY1 minus BY0 plus CZ1 minus CZ0. And that's all over the square root of A squared plus B squared plus C squared. Just make sure I left myself enough room. Move that over just a little bit. And so this is going to give me D is equal to AX1 plus BY1 plus CZ1. I'm just taking the X1s, putting them here. And then that's going to be minus, okay, minus. Now you see the AX0, BY0, and CZ0. That's AX0 plus BY0 plus z 0. Yes, it's minus on all of them, but I factored that minus out. And that's over the square root of a squared plus b squared plus c squared. All right, now, since P0 lies in the plane, okay, we can write ax0 plus by0 plus cz0 plus d equals 0. And we can see here d is equal to negative ax0 plus by0 plus cz0, right? If I move all of this over and factor out that negative, and so what does that give us? That gives us that d is equal to the absolute value ax1 plus by1 plus cz1 plus, and you see this right here, I'm replacing that with d. And that's over the square root of a squared plus b squared plus c squared. And so this is your distance formula. That gives you the distance, okay? That gives you the distance between a point and a plane. This is your distance formula. This is what you'll need to know that. All right. All right, so let's look at this example. It says find the distance between the parallel planes, this plane and this plane. So let's find the distance between them. All right. So I know it tells us that the planes are parallel. Okay, it tells us the planes are parallel. But let's go ahead and show that they're parallel. So I've got n1, my normal vector, the normal vector to this one. That's equal to what? 10 to negative 2. And normal vector n2, that's what? That's 5, 1, negative 1. All right. And now remember, we can show, okay, remember, if the normal vectors are parallel, then the planes are parallel. So we can show real easy that these are parallel. We can what? We can do the cross product, right? And if the cross product is equal to 0, that means they're parallel. Another thing we can do is look, this, if I factor out a 2, I get 5, 1, negative 1. It's a scalar multiple of this one, so that tells us that they're parallel also. Okay. All right. So what does it say? What does it say to do? Find the distance. So now we can choose any point on one plane and calculate the distance to the other plane. Okay. All right. So let's do that. So let's choose point on one plane. So I guess what we'll do here is, how about we let's choose x equals 0 and z equals 0. And let's put that in this plane. Okay? Now, is that what I got to do? No. You might be saying, well, how did you know to do that? How did you know to do that? All right, well, look, I could have said let y equal 0 and z equals 0. Then I would get 10x equal 5 and x would equal 1/2. Well, I didn't want to have to deal with fractions. So I went through and I just looked real quick and I said, well, if this is 0 and this is 0, y is 1. And so I just have to deal with the 1. That's all. Okay. If you wanted to, you could say y 0, z is 0 and plugged it into here, got x is 1/2, plugged all of that into the formula, and you would have gotten the correct answer. Okay. All right. So that's what I did. So now we have 5 times 0 plus y minus 0 equals 1. So that tells us that y is equal to 1. And so our point is 0, 1, 0. All right. So what did I use? So I used a point on this plane, right? I used a point on that plane. So I'm going to used a point on this plane. So I'm going to use this plane because I want to know the distance from the point on this plane to this plane. You see that? So there's my A, B, C, right? Take a look at our formula up here. There's my A, B, C, and plug all that in. So you know, basically what I'm doing is, let's see, where am I? Right here. So basically what I'm doing is I'm taking my point 0, 1, 0, and I'm plugging it in to this plane right here because my point's on this plane. You see that? If I were to have found a point on this plane, then I would have had to plug it into this one. Okay, so does everybody see that? It's the point you choose the plane on. It's the point you choose. Okay, that's the point. You know, what you go get a point on one of the planes, and then you take that point and put it into the other plane. All right. And so I'm running out of room again. So I get D is equal to, so that's going to be what? Remember our formula up here. That's right here. That's AX1 plus BY1 plus CZ1 plus D over the square root of A squared plus B squared plus C squared. Let me move this point up some. That's 0, 1, 0. All right, so I'm using this plane right here. Let me put it right there. Well, not right there. Stick it right there. All right. So I've got 10 times what? 0. See, I'm plugging this point into here. Plus 2 times 1 minus 2 times 0. And then the 5, I'm going to move it over, so that's going to be minus 5. I need absolute value of that over the square root of A squared plus B squared plus C squared. So there's A, B, and C. So that's 10 squared plus 2 squared plus negative 2 squared. And that equals, and when you punch all that into your calculator and you can rationalize denominator and all that good stuff, you get square root of 3 over 6. Or I guess you could just put it all in your calculator and write a decimal answer. Okay. All right, so that's the distance between those two planes. Okay, the distance between the two, I moved that one, but the distance between those two planes, that's how you would go about doing it. All right, so let's take a look. Last example. All right. So it says in a previous example, which we did that earlier, we showed that these two lines are skew. Okay, so they want us to find the distance between them. All right, so if you have skew lines and they say find the distance between them. All right, so let's think about this. So they're skew lines. That means they don't intersect. So so we know L1 and L2 are skew. So the planes that they lie in, P1 and P2, so let's say L1 lies in plane 1 and L2 lies in plane 2. We know P1 and P2 are parallel. So all we have to do to find the distance between L1 and L2 is find the distance between P1 and P2, plane 1 and plane 2. And, you know, we can do that. So what do we have to do that? All right, so let's look at this. So we have V1, the vector that's parallel to L1. Okay, so basically what we got to do to find the distance between the two planes is we got to have the equation of one plane, and we need a point from the other plane, right? So I need to get the equation of one of these planes. And to find the equation of a plane, you need what? You need a point on the plane, and you need what? The normal vector to it. So V1, that vector is parallel to this plane. That's going to be what? The vector 1, 3, negative 1, right? 1, 3, negative 1. Isn't this A, B, and C? And that's V1. Now V2, that's going to be the vector parallel to this plane. And that's going to be the vector 2, 1, 4. 2, 1, 4. So these two vectors are parallel to the planes. So I need a normal vector to the planes. So if I find the normal vector to V1 and V2, then I've got my normal vector. So how am I going to do that? Well, that's easy, isn't it? That's what? That's the cross product of the two vectors. So that's I, J, K. And so 1, 3, negative 1. Then we got 2, 1, 4. And you know, I've done the cross product enough in here, so I'm just going to do it real quick. So that's 12 minus negative 1 times I minus 4 minus negative 2 J plus 1 minus 6 times K. And so that's going to give me 13 I minus 6 J minus 5 K. All right. So this is what? What is this? This is N. That's my normal vector. All right. So what do we do here? Well, let's find an equation for plane P2. So that's going to be the plane that line L2 lies in, right? So let's let S equal 0, right? Because we need a point in the plane, don't we? So we're going to plug 0 in for S. So that's going to give me what? 0, 3, negative 3. You see that? So that's going to give me the point 0, 3, negative 3. So the equation for plane 2 is, remember the formula for the equation of a plane. That's a times x minus x0, b, which is negative 6, times y minus y0, and then c, which is negative 5 times z plus 3, or z minus z0 equals 0. And so that's going to give me 13x minus 6y minus 5z plus 3 equals 0. So this is plane P2. Okay. Now, what do we need? Now we need a point from the other plane. So to do that, I'm just going to let t equals 0 in L1. I let s equal 0 in L2. But here I'm going to let t equal 0 in L1. So I plug the 0 in for t. That's going to give me 1, negative 2, 4. You see that? So that's going to be the point 1, negative 2, 4. And so here you go. My distance. And remember, there's A, there's B, and there's C for when we plug it in. Okay, so remember the distance formula is AX1 plus BY1 plus C Z1 plus D, absolute value of that, over the square root of A squared plus B squared plus C squared. That's your formula. So I'm going to plug this point into this plane. That's this right here. And so that's going to be 13. That's going to be 13 times 1 minus 6 times negative 2 minus 5 times 4 plus 3. The absolute value of that over, and that's going to be the square root of 13 squared plus negative 6 squared plus negative 5 squared. And when you put all that in your calculator, you end up with 8 over the square root of 230, which that's about 0.53 would be your distance between the two lines. All right, so that is the end of this video. You've been with me for 2 hours now. So like I said, this is probably a 2-day lesson here. So, you know, if you watch it, well, I guess if you watch the whole thing, you've already done it, but, you know, just split it up into the 2 days. But I hope the video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see y'all in the next one. Later.